In the previous video, we saw how we can dereference objects in Java and make them eligible for garbage collection. When garbage collection kicks in, it traverses the entire object graph, finds these objects without any references and marks them as dead. Now, the garbage collector can go ahead and clean these things up. In this video, we'll dig deeper into the actual garbage collectors or the different types of garbage collectors that make this work. So, without any further delay, let's get started. Hey everyone, welcome to my channel. I'm Siben Naik and this is the second video of the Java garbage collection series. If you haven't checked the first part, go watch it where we discuss what garbage collection is and how Java breaks up the heap memory into the young and old generations to perform garbage collection. In this part, we will take a look at what are the different types of garbage collectors available in Java and how do you select the right garbage collector for your application. We will also take a look at some of the benefits and best practices in garbage collection. If you haven't subscribed to this channel, please subscribe and hit the bell icon so that you get notified of all my future videos. For now, let's start. The Java virtual machine has many different types of garbage collectors. You have simple garbage collectors like the serial and parallel GC and concurrent garbage collectors like the concurrent mark sweep and the garbage first GC. There are a few experimental garbage collectors as well which are part of the new JDKs. Let's take a look at each of them in more details. The serial garbage collector is the simplest implementation of garbage collector and is designed for small applications running on single-threaded environments. All garbage collection events are conducted serially in a single thread. When this runs, it leads to a stop the world event where the entire application is paused. Because you are running on a single-threaded application, when the garbage collector runs, the application threads are stopped. The application threads can resume their work only after the garbage collection is complete. Since the entire application is frozen during garbage collection, serial garbage collection is not recommended in a real-world scenario where low latencies are required. The parallel garbage collector is intended for applications with medium-sized to large-sized datasets that are run on multiprocessor or multi-threaded hardware. This is the default implementation of garbage collector in the Java virtual machine and it is also known as throughput collector. Here, multiple threads are used for minor garbage collection in the young generation and a single thread is used for major garbage collection in the old generation. Since this is more suitable in a multi-threaded environment, it can be used when a lot of work needs to be done and long pauses are acceptable. For example, running a bad job. Now there is another version of parallel garbage collector known as the parallel old garbage collector. This is the default version of parallel garbage collector since JDK 7 and it is same as the normal parallel garbage collector except that it uses multiple threads for both young and old generation. The concurrent mark sweep collector or the CMS collector is also known as the concurrent low pause collector. Low pause because the garbage collection pause times caused by the stop the world events are very low. In this, multiple threads are used for minor garbage collection using the same algorithm as the parallel garbage collector. However, the major garbage collection is multi-threaded as well, just like parallel old GC. But CMS runs concurrently alongside the application thread to minimize the stop the world events. Because of this high level of concurrency, the CMS collector ends up using more CPU than the other garbage collectors. If you can allocate more CPU for better performance, then CMS garbage collector is a preferred choice over the parallel ones. The garbage first collector or G1GC was intended as a replacement for the CMS GC. It is designed for multi-threaded applications that have a large heap size available, typically more than 4 GB. It is parallel and concurrent like CMS, but it works quite differently under the hood compared to the older garbage collectors. Although G1 is also generational, it does not have separate regions for young and old generations. Instead, each generation is a set of regions, which allows resizing of the young generation in a flexible way. It partitions the heap into a set of equal sized regions varying from 1 MB to 32 MB, depending on the size of the heap, and it uses multiple threads to scan them. A region might be either an old region or a young region at any time during the program run. After the mark phase is completed, G1 knows which regions contain the most garbage objects. If the user is interested in minimal pause times, G1 can choose to evacuate only a few regions. If the user is not worried about pause times or has a fairly large pause time goal, G1GC might choose to include more regions for evacuation. Since G1 identifies the regions with the most garbage and performs garbage collection on that region first, it is called the garbage first collector. Apart from the mainstream garbage collectors we just discussed, there are some experimental garbage collectors included in the JDK as well. Let's take a look at them. Epsilon. Epsilon is a do-nothing or a no-op garbage collector that was released as part of JDK 11. It handles memory allocation but does not implement any actual memory reclamation. Once the available Java heap is exhausted, the JVM just shuts down. So, if Epsilon does not do anything, why should we use it? Well, it can be used for ultra latency sensitive applications where developers know the application memory footprint exactly, or even have completely garbage free applications. In any other use case, the usage of Epsilon is discouraged. Shenandoah. Shenandoah is a new garbage collector that was released as part of JDK 12. Shenandoah's key advantage over G1 is to do more of its garbage collection cycle work concurrently with the application threads. While G1 could evacuate its heap regions only when the application is paused, but Shenandoah can relocate objects concurrently with the application. It can compact live objects, clean garbage, and release memory back to the operating system almost immediately after detecting free memory. Since all of this happens concurrently while the application is running, Shenandoah is more CPU intensive than G1. ZZC. ZZC is another garbage collector that was released as part of JDK 11 and has been improved over time. It is intended for applications which require very low latency, typically less than 10 milliseconds of pause time, and have a very large heap size. The primary goals of ZZC are low latency, scalability, and ease of use. To achieve this, ZZC allows a Java application to continue running while it performs all garbage collection operations in the background. By default, ZZC uncommits unused memory and returns it to the operating system. Thus, ZZC brings a significant improvement over other traditional garbage collectors by providing extremely low pause times, typically within 2 milliseconds. We covered so many different types of garbage collectors, but how do you decide which garbage collector is best for your application? Well, it depends on a few factors. If your application doesn't have strict pause time requirements, you should just run your application and allow the JVM to select the right collector. Most of the time, the default settings should work just fine. If necessary, you can adjust the heap size to improve performance. If the performance still doesn't meet your goals, you can modify the collector as per your application requirements. If the application has a small dataset or it will be run on a single processor with no pause time requirements, use a serial GC. Remember, serial GC is fine for small projects but not recommended for real-world applications. If peak application performance is the priority for your application and there are no pause time requirements, select the parallel GC. It can also be used if pauses of 1 second or longer are acceptable for the application. If response time is more important than the overall throughput and garbage collection pauses must be kept shorter than 1 second, use the mostly concurrent garbage collectors like CMS and G1. We learned about the different garbage collectors available in Java and how to select the right one for your application. Now, let's take a look at the various benefits of garbage collection. Garbage collection makes your code simple. You no longer have to worry about proper memory assignment and release cycles. You just stop using an object in your code and the memory it is using will be automatically reclaimed at some point of time. Programmers working in languages without garbage collection like C and C++ must implement manual memory management in their code. It makes Java memory efficient because the garbage collector removes the unreferenced objects from heap memory. This frees the heap memory to accommodate new objects. While some programmers argue in favor of manual memory management over garbage collection is now a standard component of many popular programming languages. For scenarios in which the garbage collector is negatively impacting performance, Java offers many options for tuning the garbage collector to improve its efficiency. Let's talk about some of the best practices you should keep in mind while dealing with garbage collection in Java. Besides the basic mechanisms of garbage collection, one of the most important points to understand about garbage collection in Java is that it is non-deterministic. and there is no way to predict when garbage collection will occur at runtime. It is possible to include a hint in the code to run the garbage collector with system.gc or runtime.gc methods, but they provide no guarantee that the garbage collector will actually run. If you don't have enough memory to run your application, you will experience slowdowns, long garbage collection times, top-the-world events, and eventually out-of-memory errors. This can indicate that your heap is too small, but this can also mean that you have a memory leak in your application. You can take the help of a monitoring tool like JStat or Java Flight Recorder to see if the heap usage goes indefinitely, which might indicate a bug in your code. If you are running a small standalone Java application, you will most probably not need any kind of garbage collection tuning. The default settings should just work fine. The best approach to tuning Java garbage collection is setting flags on the JVM. Flags can adjust the garbage collector to be used, the initial and maximum size of the heap, the size of the heap sections, and more. The nature of the application being tuned is a good initial guide to the garbage collection settings. For example, the parallel garbage collector is efficient but will frequently cause top-the-world events, making it better suited for back-end processing where long pauses for garbage collection are acceptable. On the other hand, the CMS garbage collector is designed to minimize pauses, making it ideal for web-based applications where responsiveness is important. Thank you for watching the video. If you liked it, please hit the like button and share it with your friends. If you have any feedback for me, write them down in the comment section. You can also reach out to me on LinkedIn and Twitter. See you in the next video.